Alright, so we're going to talk about complex operations theory, specifically the derivation of formulas for the multiplication, division, and the power property, or the power formula for complex numbers in polar form. So, let's go ahead and get started. Up until now, you know how to multiply complex numbers that are in rectangular form, such as 2 minus 5i times 3 plus 8i. Which you're going to do that by doing the FOIL, 2 times the 3 and the negative 2 times the 8i and all that stuff. So there you've got your two complex numbers in rectangular form. What we're going to focus on today is multiplying two complex numbers that are in polar form. So for instance, the number 5 cosine 20 degrees plus I sine 20 degrees, or 5 cis 20 degrees times 3 cosine 100 plus I sine 100. So this would be the equivalent of 5 cis 20 degrees times 3 cis 100 degrees. And we're going to develop a formula. So our formula in its generic form is going to be some complex number with a magnitude and a theta. So r1 cosine theta plus I sine theta 1 that is, times r2 times cosine theta 2 plus I sine theta 2. I think I forgot to put the 2 subscript right there. So since we're multiplying all four of these things, we can rearrange them however we want, and so we're just going to stick the r1, r2 out there in the front, and then do a little bit of FOIL. So cosine theta 1 times cosine theta 2. Cosine theta 1 times I sine theta 2. Then I sine theta 1 times cosine theta 2. I remember to put it there at that time. Plus the last term, I sine theta 1 times I sine theta 2, and so that I times I is going to be an I squared. Alright, now a couple things that we notice. First off, that I squared is negative 1. So I'm going to write this as cosine theta 1, cosine theta 2, and then this other term here minus sine theta 1, sine theta 2, bracket that. And then these other two middle terms, if you notice, they both have an I. So I'll pull that I out, I'll factor it out, and have sine theta 1, which was this right here, cosine theta 2, plus cosine theta 1, sine theta 2, and we'll bracket that as well. Now if you remember from your trig formula chart, this expression right here, if you have cosine and two angles and they're different angles and then minus the sine of those two angles, the product that is, then that is equivalent to the cosine of the sum of those two angles. And this over here is the sum formula for sine theta 1 cosine theta 1 cosine theta. So this is sum of the cosine of the sum and the sine of the sum. And this is actually our formula right here. I probably should have boxed it or something. Whenever you have two complex numbers in polar form and you are multiplying them together, then the result is the product of their magnitudes and then the sine and cosine of the sum of the angles. So that's pretty cool. So back to our example, 5 cis 20 degrees times 3 cis 100 degrees. It's going to be just the 5 times 3 and the 15 and the 20 plus the 100. So that's going to be 15 cis 120. That's great. This is a really amazing feature of complex numbers in polar form, that when you're multiplying them, you don't have to go back and forth and do all that transition, converting them to rectangular form and do the FOIL and yada yada yada, Pythagorean theorem, inverse tangent. That's it. This is great. We're now going to do something similar for dividing complex numbers in polar form. So this is how you divide complex numbers in rectangular form. You basically rationalize the denominator, or that is by multiplying by the conjugate of the denominator. So 7 plus 6i over 7 plus 6i, and then you go ahead and go through all that rigmarole. So what we're looking at now is something like 7 cis 80 degrees divided by 4 cis 45 degrees. So we've got the magnitude and the angle there for our complex numbers. So writing this in sort of generic form, r1 times cosine theta 1 plus I sine theta 1 divided by r2 cosine theta 2 plus I sine theta 2. We're going to sort of begin the same way that we normally would with our numbers in rectangular form, and we're going to multiply, in this case, by the conjugate of the denominator. So by cosine theta 2 minus I sine theta 2 in the numerator and in the denominator. Remembering that anytime you have any number divided by itself, it equals 1. So this right here is basically 1. And over here on the left-hand side, if we take any number here and multiply it by 1, we end up with the same number, though it does look different. So, time to FOIL, friends. So R1 over R2, that kind of stays the same. Over here, we're going to have cosine theta 1 times, oh, I've got to erase this, and then I really don't like that there, so let's try to make this nice and clean. Cosine theta 2, and then minus I sine theta 2 times cosine theta 1, and then this term, so the I sine theta 1 times cosine theta 2, and then a minus I squared, since we have an I and I, sine theta 1 sine theta 2. Just barely squeeze it in there. All right, good job. In the denominator, you can see we have an a plus b, a minus b situation, which turns into an a squared minus b squared term. So it's going to be cosine squared theta minus, and the second term when we square it, it's going to be I squared sine squared theta 2. I forgot to put the theta 2 right there, but you know what I'm talking about. Now, one thing we noticed, minus an I squared, just like in the previous problem, that turns into a plus. So we're going to keep the R1 over R2 and then rewrite this numerator. We'll keep that cosine theta 1, cosine theta 2 there. We'll put plus sine theta 1, sine theta 2, plus, I'll write this term right here, the I, factoring out the I guess, of each of these, sine theta 1, cosine theta 2, and then minus sine theta 2, cosine theta 1, putting that right there. And then in the denominator, also notice that minus I squared turns into a plus, so we have cosine squared plus cosine squared theta plus sine squared theta. Now in the numerator, once again, we notice that this is the sum property, or sorry, the difference property of cosines. And over here we have the difference property, or difference formula of sine. The denominator of sine squared plus cosine sine squared plus cosine squared equals 1. That's the Pythagorean identity. So probably should have boxed this too. This is super huge. There it is. Look, if we have two complex numbers and we're dividing them, then the result is just the division or the quotient of the magnitudes and the difference of the angles. So going back to our example, 7 cis 80 degrees over 4 cis 45 is just going to be 7 over 4 cis 35, or 35 is the difference between 80 and 45. That's great. This is really going to speed up our division of complex numbers in polar form. Last thing we're going to look at here is when we have a power of a complex number. So we'll start off real basic, r cis theta squared. So we know that's going to be r cis theta times r cis theta. And from our product rule, or whatever you want to call it there, we saw that would be r squared, because r times r, and then cis theta plus theta. So r squared cis 2 theta. Well, just to save ourselves some time, we can say similarly, r cis theta to the n is going to be r to the n cis theta times n. That's it. That's a really powerful property. All of these are great. And if you watch another video, we'll apply those to some particular problems. Thanks for watching.